wanted to take Ryan Greenblatt's SOTA approach on the public ARC AGI challenge and see if we could add more hints in the prompt about potential solutions through like a variety of methods, and see if adding those hints somewhere in the context or somewhere in the chain could optimize the result in some way that was meaningful. So we did a lot of exploration, a lot of it was really cool. We're excited to present our results with you guys.
So yeah, so this is the challenge. I guess Mike already introduced most of it, but the description is very simple. So each one of these is a problem, and then you're given some example inputs and outputs, and your task is to guess what the output shape should be for the last example. And the idea is that you need to figure out a kind of a rule set that applies to the kind of training set or given examples, that you simply apply to the last example and then you generate the shape.
Yeah, I'm just gonna jump ahead real quick because that's an easy example. This is a hard one.
Right.
Our team and actually George Hart spent like 25 minutes like trying to figure this one out. And it's pretty hard. So yeah, we're trying to figure out how to crack those more than these, but they're all like fun to solve.
It's also quite hard.
Yeah, it's also quite hard, yeah. Yeah, please go ahead, yeah.
And so the approach, kind of direction we took is that there's kind of multiple parts to the problem, right? So one is that you need to figure out what's the grid in the output. So sometimes the grid is the same as the input, but other times the grid of the output solution actually varies depending on the shapes in the input. And so that's one problem. Another problem is figuring out what the actual shapes in the output are. And the third one is figuring out the color of the shapes. So if we, yeah, exactly. And then like different numbers of colors, right? And then, so if we figure out all these parts of the problem, we have basically solved the whole problem. And so this is kind of some examples of where you got an input and grids in the output are highly non-trivial. So for example, here, the kind of, well, here is just a kind of a one-dimensional grid, but the number of squares in the output is actually equal to the number of different regions in the input shape.
Wow.
Right? So we got 4 regions on the first one, 2 regions, and then 3 regions there. So there's some examples of the particles.
And yeah, so in order to basically tackle some of these harder, like grid-based transformations, we first of all defined some really simple transformations. As you can see here, a lot of it is just identity, square, taking root, divide by 2, transpose, etc. And then we also defined some custom heuristics over these that specifically look at the previous like 3 or 4 examples that were given, and then we evaluate those heuristics based on the test inputs and outputs. And so just with these collection of heuristics, we were able to get about approximately 86%. Okay, so we should update this. We should update these numbers. So approximately, we were able to just literally using heuristics get about 86% on the grid size. Yeah, evaluation.
To guess the grid size.
So you guess the grid size programmatically
Yeah.
86% of the time, and we figured that was a really great hint to drop in.
Yeah.
So the second part of the problem is the part that I worked a bit more on, which is getting into how Ryan Greenblatt's solution actually works. The man's a genius. He wrote it in 4 days. It's battle tested. It survives rate limits. Like, it's meant to be submitted to Kaggle and so run for hours on its own. But on the other hand, it's like, we were calling it a GPT-4.0 casino because, it just takes like, between 25 and 60 starting prompts, injects a bunch of, there's like 8 basic variants, and then it injects few shot examples using like an algorithm I still don't fully understand, although I'm getting closer. And then it forms like this huge set, it dismisses some of them, and for every single problem, it starts with 25 to 60 prompt chains of about 30K tokens each. And it goes to, I think, 10 steps in each chain, repeatedly extracting the Python code and seeing if, when you see the ARC challenge, every problem is given 3 examples with the solution. That's known as the test set. And then you're given a final, that's known as the train set. And then you're given a test problem as well with no provided solution, right? And so the prompt like looks at the 3 tests, writes a program to solve them, runs it on the train, and presents it to you like a prospective solution. It actually presents 3 prospective viable solutions from this big map because you're allowed to try it 3 different times.
So what makes it a little bit more non-deterministic is that you run all of these with very high temperature.
0.9.
So in our evaluations, we found that, you know, for even the same problems, we sometimes would end up with completely different solutions. So.
Yeah. So yeah, and also the cost. So, you know, when we started out, we were like a bit scared of like the cost, but I was like, no, we should go ahead anyway. And then I discovered I have hundreds of GPT-4 tokens, OpenAI tokens expiring tomorrow. So that was really a little bit of magic. And so we spent like $500 like trying this over and over. And basically we I mean, God's grace, you know. And so we AI research the holy way. So we injected just this line into all the prompts because we already knew the final grid size for the set that we were testing because we had both the problems and the solutions. So instead of using the heuristics we developed, we just literally injected like the final grid solution size, and we wanted to see if it would work or not. Our intuition was it would be a powerful hint because 86% of the time you can tell, especially in very hard problems like this one, it's like really crazy. And here actually, just so you guys know, the size of the blue is the size of this. So whatever size the blue thing is, that's the size. It's really hard.
Yeah.
So we figured it's like a really strong hint. But injecting that prompt into Ryan's examples on the sets that we tried, every time we got the same results. And we tried 3 different sets of 10, 10, 10, 10, and then 6 and 6. In the 6, we cherry picked problems where like we knew that the sizes would change. It takes about 84 seconds per problem, and you can't run them in parallel because of the amount of tokens. So, you know, it takes like, you know, a minute and change for each one. So yeah, we ran a bunch of them, and we did establish that giving the hint about dimensions on this size, you know, wasn't a clear signal. But we did prep a bunch of other hints that we did not have time to test. So our collaborator Shaw's been spending a lot of time on this problem, really a genius, and he wrote another library that actually looks at problems and comes up with all these different hints. One of them is how the matrices transform. Another one is the actual shapes within and like where they are. And also there's relationships between the colors before and after. So in the art challenge, one of the crazy things is there's objects, and you kind of have to detect the objects, and they're hard to detect because there's no like formula for detecting them. And there's input objects and output objects, and they have relationships. And the relationships can be shape, color, size, or any other combination thereof. So, you know, that was our intuition. And then we also prepared some other shape detection algorithms and denoising, but we didn't get to try any. But fortunately, I still have like $200-300 credits left. So tomorrow, I'm definitely going to give it, you know, another go with a few more because the approach seems really viable, and we're excited to find out if we can find something that gives a clear signal. Thanks.